Good day, everyone. Today we'll be presenting one of the frameworks that can guide educators in meaningfully incorporating technology into our instruction, moving from basic tool use to transformative learning experiences. Let's begin by understanding why this topic is so important for math education today. The challenge that we face is clear. Effective technology integration requires more than just using the latest tools. Simply having tablets, smart boards, or educational apps in the classroom doesn't automatically lead to better learning outcomes. What we need is a structured approach. Educators need a framework to, first, evaluate current practices, or we should ask ourselves, where are we now in our technology use? Second, plan meaningful learning experiences, or how can we design lessons that truly leverage technology? And last, progress from basic to transformative use, or how do we move beyond substitution to genuine transformation? This is where the technology integration matrix comes in. TIM, developed by the Florida Center for Instructional Technology at the University of South Florida, provides the solutions to these challenges. It provides a comprehensive framework that focuses on teaching and learning practices, not just the technology itself, and student-centered learning, shifting from ownership of the teacher to the learner. The framework consists of 5 characteristics across 5 levels, hence resulting in 25 integration states. This matrix gives us a roadmap for progressively integrating technology in ways that enhance learning.
Now, let's explore the framework in detail. Here, you can see the complete technology integrated matrix. As mentioned, it has two main parts. Along the horizontal axis, we have 5 levels of technology integration. Whilst on the vertical axis, we have also 5 characteristics of meaningful learning environments. Each cell in this 25-cell matrix describes a specific state of technology integration. The framework helps us understand not just whether we're using technology, but how we're using it and what kind of learning environment we are creating. Now, let's focus first on the 5 levels of technology integration, which are entry, adoption, adaptation, infusion, and transformation. So, these levels represent a journey from teacher-centered, basic technology use to student-driven, transformative application. So, understanding these levels help us set realistic goals and plan our growth as educator. Now, let's examine each level in detail. So, the first one is entry. Basically, this is where the teacher begins to use technology tools. Take note of the word use to deliver curriculum content to students. At this level, technology serves primarily as a presentation tool. For example, a teacher projects educational videos. Second, a teacher uses PowerPoint slides to present lesson. Diba? And another one, student watch demonstration on a smart board. So the key characteristic is that students are passive recipients. So technology is used by the teacher rather than with student. While this is a starting point, our goal is to progress beyond this level toward more active, student-centered uses. Okay? So yun ang entry. So the second level is adoption. The teacher directs student in the conventional and procedural use of technology tools. At adoption, student begin using technology, but in highly structured, teacher-directed ways. So here are examples. Ayan. Student following step-by-step tutorial. Second one, using real and practice software. And next, completing predetermined activities with specific tools. So the teacher still controls what tools are used and how they are used. So students follow direction but don't yet make independent choices about their learning. This is necessary developmental stage as students learn to use tools properly. Okay? Now, for the third level is adaptation. Essentially, the teacher facilitates the student exploration and independent use of technology tools. This is where meaningful change begins. At adaptation, yung pangatlo, the student have choices in how they use technology. They can already explore and experiment with tools. Also, their independent use is encouraged and supported. For example, a student might choose between different math apps to solve problems or explore a concept using interactive simulation at their own pace. So here, the teacher shifts from director to facilitator, hence creating a space for student agency. Okay? Now, the fourth level is infusion. This is where the teacher provides the learning context and the student choose the technology tools. At infusion, technology becomes seamlessly integrated into regular practice. Basically, the student regularly and independently select appropriate tools. Technology use is also student-initiated and based on the task. The teacher sets learning goals while students determine their path. For instance, when assigned a data analysis project, a student might independently decide to use Excel, Google Sheet, or graphing calculators based on their needs and preference. To put it in a capsule, technology has become a natural, expected part of learning environment. So, the last level of technology integration. Let's move on. The last level is transformation. This is where the teacher encourage the innovative use of technology tools. Ito na yung panglima. To facilitate higher order learning activities that may not be possible without the use of technology. This is the ultimate goal of technology integration. At transformation, technology enables learning experiences that couldn't exist without it. So, students engage in innovative, creative application wherein higher order thinking skills and problem solving are central. In short, learning extends beyond classroom boundaries. Extension. Example include student collaborating with peers globally on real-world problems. Second, creative interactive mathematical demonstration. Pangatlo, engaging in citizen projects using data collection apps. So, the key question at this level is, could we do this without technology? If the answer is no, then we have reached transformation. Okay? Now, let's turn to the vertical dimension of the matrix, which are 5 characteristics of meaningful learning environment. These characteristics describe the nature of the learning that is happening, regardless of which tools are being used. These aren't mutually exclusive as the most powerful learning experiences often embody multiple characteristics simultaneously. So, one of those characteristics is active learning. So, this is where students are actively engaged in using technology as a tool, rather than passively receiving information from the technology. This characteristic distinguishes between passive, like watching a video about fraction, and active, like manipulating virtual fraction tiles to discover equivalent fraction. The key question is, are students doing something with technology or are they just receiving from it? Active learning means students are manipulating, exploring, creating, and experimenting. In other words, they are mentally and physically engaged with the tools and the content. Another one of the characteristic is collaborative learning. This is where students use technology tools to collaborate with others rather than working individually at all times. At higher level of this characteristic, students work together using shared digital workspace. They give and receive feedback through technology. They also co-create using collaborative tools. They may connect with peers beyond their classroom. Collaboration doesn't mean students are always working together. Individual work has a value, but technology should enable and enhance collaborative opportunities when appropriate. Next, we have constructive learning. This is where students use technology tools to connect new information to their prior knowledge rather than to passively receive information. Here, students build their own understanding through active engagement and connect new concepts to what they already know. For example, rather than being told the formula for the area of triangle, students use digital tile arrays to discover the relationship themselves, which can build their understanding from the ground up. Another characteristic is authentic learning. This is where students use technology tools to link learning activities to the world beyond the instructional settings, rather than working on the contextualized assignment. This characteristic asks, does this matter outside school? Authentic learning might involve analyzing real data sets from scientific research, solving actual community problems, and communicating with real audiences. When mathematics connects to real-world context through technology such as weather data, sports statistics, economic trends, and students see purpose and relevance in their learning. Lastly, we have goal-directed learning. This is where students use technology tools to set goals, plan activities, monitor progress, and evaluate results, rather than simply completing assignment without reflection. This characteristic emphasizes metacognition, which is thinking about thinking. Students should set their own learning goals, plan their approach to tasks, monitor their progress using digital tools, evaluate their own learning, and adjust their strategies. For example, students might use digital portfolios to track their growth over time, set personal mathematics goals, and reflect on their learning strategies. So once again, there are two main parts in the matrix. So if those are combined, there are 25 integration states. Let's look at a specific example for the matrix. From the matrix, we have here constructive adoption. This cell combines the constructive characteristic, wherein students to build their own knowledge, and the adoption level, which is teacher-directed structured use of technology. In practice, this means students use teacher-directed technology in structured ways to organize data, explain relationships, and build understanding rather than just receive information. A mathematical example is this. The teacher guides students through using a graphing calculator To explore the relationship between equation of a line and its graph, students follow specific steps but make their own discoveries about how changes in slope and y-intercept affect the graph. This demonstrates that even at a lower integration levels, which is the adoption, we can design activities that promote meaningful learning or constructive. Okay?
Moving on to the application of the framework. Looking through the most recent curriculum for basic education in the Philippines, which is the Matatag curriculum, we were able to find the following learning competencies that could be taught with technology. However, in this presentation, we would just highlight 3 of them. So the first one is making models of solid figures, which is a competency in grade 5, 4th quarter under the domain Measurement and Geometry. A possible ICT tool that can be used to teach this is Polypad by Amplify. An example of a classroom scenario is when the teacher demonstrates how to construct solid figures using their 2D nets. Using Polypad by Amplify, the teacher can display a cube and unfold it to show its net, which is 6 squares arranged with 4 in a row and 1 each on the top and bottom. This tool can effectively provide a clear and dynamic way to visualize spatial relationships, as students can see in real time how a flat net transforms into a 3D figure, which is something difficult to show through static drawings. This integration is considered at the entry level of the technology integration matrix because the technology is used by the teacher to deliver content. The teacher operates the tool while the students just observe the demonstration rather than interact with it themselves. Furthermore, the lesson does not demonstrate any of the 5 TIM characteristics. It is not active as the students watch the demonstration rather than manipulate the tool themselves. It is also not collaborative since the students do not work together using the technology. It is also not constructive because the teacher explains the relationship between nets and solids instead of the students building understanding through hands-on exploration. It is not authentic as the technology use is limited to a classroom demonstration rather than connected to real-world applications. Finally, it is not goal-directed because the teacher controls the process and the students do not set goals, plan, monitor, or evaluate their own learning. Although this level involves passive participation, it still remains a valid and useful starting point for integrating technology. It can enhance understanding by making abstract geometric concepts more visual and accessible, even if the students are not yet directly manipulating the tool. The second competency is plotting points on the Cartesian plane and determining the coordinates of a point, which is under grade 8, 2nd quarter, with the domain number and algebra. The possible ICT tools that can be used in the classroom are Desmos, GeoGebra, 𝐌𝐀𝐓𝐇𝐄𝐌 coordinate board, and MathsFrame coordinates alien attack. In this particular context, the students are tasked to work in pairs on a 2-part coordinate exploration activity. First, they are assigned to specifically use 𝐌𝐀𝐓𝐇𝐄𝐌 coordinate board on a device to practice plotting and naming points. Each pair receives coordinate pairs to plot across different quadrants and axes. The partners take turns placing points using the drag and drop feature and verify accuracy using the show or hide coordinates option. Whilst they are doing this, the teacher moves around the classroom to provide support. With the same partner, they move to MathsFrame, coordinates alien attack, which is a gamified formative assessment. The students once again collaborate to identify and enter the correct coordinates to hit the targets. These tools are effective because they provide interactive visualization and instant feedback, which can help students quickly correct errors and strengthen their understanding of coordinate relationships. The drag and drop interface of Braining Camp and the game format of Maths Frame can increase their engagement, support differentiated pacing, and build student mastery. This reflects the adaptation level of TIM because students actively and independently use the assigned technology within a structured task. The teacher provides guidance, but students collaborate, make decisions within the activity, and learn through hands-on exploration rather than following strict step-by-step procedures. Furthermore, the lesson demonstrates several TIM characteristics. It is active, as the students directly manipulate and plot points using the digital tools. It is collaborative, since they work in pairs and support each other throughout the tasks. It is constructive, because the students build their understanding through immediate feedback from the ICT tools. Lastly, it is goal-directed, as they monitor their progress through game levels and adjusting their strategies accordingly. The authentic application remains to be limited in this context because students are working with practice-based tasks rather than real-life situations, which is just appropriate at this stage of technology integration. The last competency is using appropriate graphs such as pie graphs, bar graphs, line graphs, and stem and leaf plots to represent organized data. So this is a grade 7 third quarter topic under the domain Data and Probability. Possible ICT tools include Excel and Google Sheets. In this classroom scenario, the students act as consultants addressing a real issue, which is long canteen lines during the 20-minute grade 7 break. The teacher, as suggested by the canteen manager, has asked students to investigate the problem and propose data-driven solutions that the school can implement. The project unfolds in phases. First, the groups identify key questions about food preferences, peak arrival times, preparation speed, and payment methods. They design and distribute surveys using perhaps Google Forms to easily collect anonymous responses from all grade 7 sections. After gathering the data, the students organize it in any spreadsheet and data visualization tool, compute basic statistics, and create appropriate graphs. The students then interpret their findings and develop practical recommendations. For example, if most students arrive within the first 5 minutes, they might suggest staggered break times. Finally, teams present their graphs, analysis, and recommendations to their teacher, canteen manager, and other school representatives, wherein they defend their recommendations using data. These tools are effective because they allow students to efficiently collect large-scale data, analyze responses, and generate multiple visualizations for comparison. Technology enables them to conduct meaningful research and communicate their findings clearly and professionally. This reflects the transformation level because technology makes an authentic investigation possible, where students analyze real data and propose solutions that may influence actual school decisions. The task goes beyond textbook graphing and becomes applied community-based problem solving. Additionally, this project demonstrates all 5 characteristics. It is active, as students design surveys, analyze datasets, and create data visualizations. It is collaborative, as teams work together and engage with school stakeholders. It is constructive, as students interpret data and build evidence-based recommendations. It is authentic because the problem directly affects their school community. Finally, it is goal-directed, as students set research questions, monitor their analysis, and justify solutions using evidence. To conclude, the Technology Integration Matrix provides educators with a powerful framework for meaningful ICT integration in education. Our key takeaways for this are the following. First, technology integration is a progressive journey. The 5 levels, entry, adoption, adaptation, infusion, and transformation, show us that we don't need to reach the highest level immediately. Every level has value, and understanding where we are helps us plan our growth intentionally. Second, focus on learning, not just tools. The 5 characteristics, active, collaborative, constructive, authentic, and goal-directed, remind us that effective integration is about how technology enhances learning, not just which devices we use. Third, transformation happens when technology enables what was previously impossible. Our examples showed this progression, from teacher demonstration with Polypad, to student exploration with graphing tools, to authentic problem solving with real data and graphs. At each higher level, students gain more autonomy, make more choices, and engage in more meaningful problem solving. The TIM framework transforms our question from what technology should I use to how can technology create meaningful learning experiences that engage students in active, collaborative, constructive, authentic, and goal-directed learning. By thoughtfully applying this framework, we can ensure that technology truly enhances student understanding and prepares them for the increasingly digital world they'll navigate.